Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Okay, today we're revisiting problem number 3.43. My previous video had a pretty significant error to it, where I neglected the density of water when the density of water was comparable to the manometer fluid. So I'm going to go back through this problem and point out the error that I made and make the correction here. Thank you to the viewer who pointed out this error that I made. All right, so this is out of the Elementary Principles of Chemical Processes, 3rd edition, and like I said, it's problem number 3.43. I'll read the problem statement. A fluid of unknown density is used in 2 manometers, one sealed end and the other across an orifice in a water pipeline. The readings shown here are obtained on a day when barometric pressure is 756 millimeters of mercury. What is the pressure drop in millimeters of mercury from point A to point B? Okay, so in part A, we're in the beginning part of this anyway. We have this set up here. And what we need to do is to calculate what the density of this manometer fluid is. We don't know what it is at this point. And so we're going to use this manometer to calculate what the density of our manometer fluid is, and then we're going to use that calculation in order to solve this problem, to figure out the pressure drop across the orifice there. Okay, so they gave to us that the atmospheric pressure was 756 millimeters of mercury. I'll convert that into pascals so that it's easier to work in these units. And then I look at, okay, what's the pressure at PC, point PC? Well, we assume that the atmospheric pressure goes all the way down to this point. In reality, there's a density gradient from this point up top down to this point. However, there's like a pressure head there. However, the pressure head of a gas is way smaller compared to a liquid, and so usually we neglect that. So we'll say the pressure at this point is the atmospheric pressure. So 7.23 meters of head pressure from this. Usually there is a vapor pressure here as well, but that vapor pressure is usually very small, and so we can assume that it's 0. Okay. The pressure at point C on the left is equal to the atmosphere, like I said, and then on the right, it's equal to the head pressure. So we can calculate what the density is just by rearranging this equation as so, and then we calculate that the density of the fluid is that. Okay? Now here's where I made my error. In this part, I said that the pressure at point PA is only equal to the head pressure difference here due to the manometer fluid. However, if we look closely, this pipe is no longer filled with air, it's filled with water. Okay, so this leg is filled with water, so there definitely is a pressure head there difference due to the water. And I neglected that when I first did this problem, so make sure you make this correction if you're doing this problem. That you account for the pressure head of the water on the left leg. Okay? So this analysis is not correct. This analysis is correct. That the pressure at point A is equal to the pressure at point B plus the pressure head here minus the pressure head that's on this side due to the water. Okay? So we have pressure at point B plus the pressure head due to the manometer fluid minus the pressure head of the water on the other side. So then you get, when you calculate what the pressure difference is, you get this equation and solve it, get pascals, and then convert that into millimeters of mercury like they asked for. Well, that is it for problem number 3.43. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.